Welcome. The title of today's notes worksheet is Rational Inequalities. This is simply a continuation of the previous lesson dealing with polynomial inequalities, but there are a few more things that we have to be concerned about with the rational family. So we'll go ahead and have to develop a few ideas before doing a few examples to back it up. And we should follow a very similar process, though, to yesterday's lesson. So let's do a little graphical investigation to get us thinking in the right direction here and get those conclusions taken care of. So here we go. It says at the top, determine the intervals, so everything of course will be expressed in terms of x, for which the function values, the y values, are positive. So graphically, if you remember what that meant, is just we're looking for where the graph is above the x-axis. If you remember on yesterday's lesson, I did both positive and negative. In this case, there's no reason to do both. Let's just do positive here. But there is one thing I want you to think about as we go through this process, is what is separating the function values, the positive versus negative. Yesterday, it was just the x-intercepts. Today, maybe not. All right, so let's go for it. Here we go. Everyone type in just 1 divided by x, just the most basic rational function out there. I'm going to hit zoom in number 6, and we get our nice looking hyperbola. Not a big deal right there. 2 branches, and just to get this going along nicely, it looks like this branch of the hyperbola, which would be to the left of 0, by the way, to the left of 0, seems to be below the x-axis. And it looks like this branch of the hyperbola seems to be above the x-axis, and this one seems to be to the right of 0. And so I have a feeling what we're going to do is express our inequality as x is being greater than 0. Anywhere where x is positive, it looks like y is also positive. And if you look at the function, that should make pretty good sense. Now, just one thing to note here. What is really separating the negative values from the function values as I move left to right? Well, if you notice, I'm going down, closer and closer to this vertical asymptote. Then when I jump over the vertical asymptote, that's when I go from negative to positive. So it's not an x-intercept here. It happens to be a vertical asymptote. All right, well, let's get this taken care of. X is greater than 0. Looks perfect. All right, next one. Let's go get it set up, everyone. I'm going to go back to the y equals, and I have negative x minus 5, and then divided by x plus 3. Okay, nice. I'll hit graph. So similar situation. Look at where the graph is above the x-axis. Think about that for just a sec. Here is obviously the function. Placed graphically, looking good right there. Jump over, come back down here. And by the way, this does level off below the x-axis. So I'm envisioning it, and see if you agree on this, I'm envisioning just above the x-axis only from here to here, as a matter of fact, just between those two values. And this seems to be an x-intercept at 1, 2, 3, 4, negative 5. So it looks like to the right of negative 5, we're above, we're above, we're above. And then it's going to keep going, shooting up, getting closer to this vertical asymptote at negative 3. But once we jump over that negative 3, we're back down here below the x-axis. And so I'm only seeing it between those two values, between negative 5 and negative 3. I hope you would agree with that statement right there, because that's how I'm going to place it, between negative 5 and negative 3. Okay, now, just one thing to note before we do that last one. Look at the two things that separated positive and negative. Here as I go left to right, negative, but then it hits the x-intercept, and now it changes to positive. So that was a boundary point right there. Also, as I continue, I go, and then I jump over the vertical asymptote, and that's what changes positive to negative right there. So two situations that were boundaries between positive values and negative values. One an x-intercept, and one a vertical asymptote. Alrighty, cool. Let's go get that last one taken care of. I'll be fairly quick on this. You can just watch this one. I'm going to have to change the window on it anyway, if I remember this one correctly. So I'm going to just go right there, and let's see. I'll keep that. Do something like this right here. See if that's decent. Yeah, it's not bad. Kind of get a little bell-shaped curve. And by the way, we are above the x-axis all the way through. You've got a horizontal asymptote at y equals 0, so it is staying above the x-axis as we go left to right from negative infinity to infinity. So in terms of where the function values are positive, well, any x value will make the function value positive. So all real numbers. And again, those expressions should look familiar from the previous lesson. These are the types of solution sets we're going to see when we solve algebraically. All right, let's get this conclusion in place. So it's all based on the idea of boundary points. On the polynomials, it was just the x-intercepts. In this case, and again, I'm going to put this in quotes here because it's not perfectly going to be aligned. So the boundary points, so to speak, that we saw yesterday can come, they don't definitively come, but they can come from the numerator. And if you remember, the numerator in a rational function is what produces the x-intercepts. So potentially, we're going to see the boundary points come from the numerator. And also, here's the key, we're not only seeing boundary points from the x-intercepts, but also from those vertical asymptotes, and they come from the denominator. And so let me get that squared away right up here, because the denominator is going to potentially produce a boundary too. And so let's write it in as the vertical asymptotes right here. Okay, that looks really nice. You see why I kind of put this in quotes, because obviously a vertical asymptote is not a point, but it kind of serves the same purpose as what we saw yesterday. So it is potentially a boundary separating negative from positive, and that's what we want to focus in on when we do some sign charts. Okay, great. I hope that first conclusion makes pretty good sense. We'll see that in place momentarily. Let's do one other situation here. And it says, what would be your first step in solving the rational equation? And underline that for me if you would. So let's just take a step back and deal with this as an equation. Then we'll talk about the inequality aspect of it. So guys, what would be your first step? If I gave this back, I think we saw this early in the semester. What would you do to solve this particular equation right here? Well, I'm hoping you would agree that in some way, shape, or form, we would eliminate the fraction, kind of bring up that x plus 3 to the other side. Basically, we would just cross multiply. But in essence, I would multiply this side of the equation by x plus 3 and that side of the equation by x plus 3 to eliminate the denominator. And that would be a pretty good goal right there. And we wouldn't have too many issues around it. So again, there are a couple different perspectives on it. But I'm going to write it like this. Multiply both sides of the equation by x plus 3. That would eliminate the fraction, and then it just changes it to a nice linear equation, and we can solve without too many issues. We would be careful of creating an extraneous solution, but again, that's not the issue at hand here. All right, so that's what we would do in a rational equation. Now, guys, let's take a look at this. There's a little red flag, though, when we change it from an equation to an inequality. So it says we have to be careful when solving rational inequalities. For example, if you look at this rational inequality right here, notice it's the exact same thing, but instead of equals, I just put a greater than symbol. It is very tempting to multiply by x plus 3, just like we did right here, and to eliminate the fraction. What is the problem with that step? The question is, why can't we do it here in the inequality when we could do it in the equation right up here? So you might have to think back to your work on inequalities, but I'll give you a second. I'll stall for a moment while you think about it. Why not here when we could do it here? Well, here's the issue. And don't write this on your paper because I'm going to erase this momentarily. If this wasn't x plus 3, so for example, if this was just a 3, and again, don't do this on your paper because I'm going to fix that momentarily. If this was a 3, it would not be a problem at all. I would multiply both sides by the 3, and I would go for it. Wouldn't be a problem. Guys, if this was a negative 3, same deal. If this was a negative 3, I wouldn't have any issues at all. I would multiply both sides of this inequality by negative 3, but, and remember your rules on inequalities, if I multiply both sides of an inequality by negative 3, what do I have to do to the symbol? Change it. I have to change the symbol. So if this is a constant, I know exactly what to do with that symbol right here. If it's a positive, I keep the symbol. If it's a negative, I change the symbol. But if you notice, I don't have a constant down here. What I have is a little linear factor, so to speak, a little linear divisor, and I don't know what to do. Because for certain values, this would be positive. For other values, this would be negative. And so as a result, really the question is this positive or negative? Well, in essence, it's both. For certain values of x, it's positive. For other values of x, it's negative. So do I know definitively whether or not to switch the symbol? No. And that's the problem at hand here. There's no definitive way to deal with that inequality symbol. And so as a result, we can't just go ahead and multiply by the x plus 3. It just doesn't work, unfortunately. So I'm just going to write a couple things here, and then what we're going to have to do is kind of find a way around this. So I guess, the question is x plus 3, positive or negative? And do we switch the symbol or not? It is not definitive by any stretch of the imagination. So let's get that in place. And let's find our way around it. Okay, so because we can't just do that, and again, it would be nice if we could, we have to find some strategies for dealing with it. And so I've just wrote a few down. Obviously, you can kind of take a look and take them for what they're worth. I'll go ahead and do a little read through, and then we'll try just our examples with this. The key, of course, is set the inequality to 0 if it's not already. So remember, that's what we want to kind of talk about. Greater than 0 will be positive. Less than 0 will be negative. And then what we're going to have to do is combine it into a single rational expression. So combine the fractions, again, if necessary. And then what we developed, everybody, is finding the boundary points. But in this case, what we found is the boundary points come from the numerator, x-intercepts, and the denominator, vertical asymptotes. And then obviously we just follow the steps from yesterday. At that point, it really becomes basically the same piece. So I'll let you kind of absorb that, process that a little bit, and then let's go ahead and try example 1. So here is that example. Same one that I put on the front side, and I said, we cannot multiply by x plus 3, and it is unfortunate that we can't do that, but there's no real definitive way to pull that off. So let's go to our nice plan B. Some good math here and good review on some skills that we've seen before. So let's give this a try. First order of business, set it to 0. So minus the 2, and if it's okay with you, just because I'm dealing with fractions, I'm going to put it over 1. You definitely do not need to do that by any means. But I'm going to do that piece right here. And now it's set to 0, so I hope everyone's okay with this. When all said and done, I want to know where this is positive, so greater than 0, positive. One thing I have to do first, though, is put those fractions together. So let's create a single rational expression out of it. Common denominator, everybody, is x plus 3, of course. So let's go ahead and see this in action. Remember, old denominator, new denominator, did not change. So the numerator doesn't change there. Just be a little careful with minus. You know the drill on this. So I like putting that in parentheses on the back end, after a minus especially. And then how did you change denominator, old to new? Looks like I multiplied that by x plus 3. So let's multiply the top by x plus 3. Something like that would do. Again, all greater than 0. All right, clean that up if you get an opportunity. I'd ask you to do it before me, so I'm going to go ahead and obviously keep our denominator. But guys, see what happens on that numerator if you would. Let's make sure we all get that same thing. And obviously then, single fraction, and we're looking for where it's positive. So I get a 1x minus a 2x. So I get a negative 1x, by the way. And then I get a 1 minus 6. So that would be negative 5. So I'm getting that piece right there. And now we're going to take exactly that and roll with it. So same deal as yesterday. So boundary points, everybody. And just if you need to, you don't have to do this on your paper if you don't want, but boundary points come from the numerator. So I would kind of look at that. Also, boundary points come from the denominator, so I'd look at that. And if you solve this one right here, I believe you get -5 as a boundary point. And if you solve this one right here, of course, you get -3 as a boundary point. So now I can come right up here. Again, one big distinction between yesterday and today. Boundaries come from the numerator and the denominator potentially. So I've got -5 and -3. And now it's just yesterday's lesson in a nutshell. So I just do this to orient myself, nothing more. So I've got -5 to the left, -3 to the right. That looks really good. And then let's go ahead and do our 3-column system here. Interval. Factors there. And actually, let's do this a little differently than what we saw yesterday at least. So the numerator was this, and denominator was this, kind of in factored form. So that's how our factors are played out, really with division as opposed to multiplication like we saw yesterday, and in the outcome. Okay, so let's get it going. To the left of -5, between -5 and -3, and bigger than -3. Looks great. Now let's make it happen. So what we want to do is just see what happens to the numerator, what happens to the denominator, and then what would be the overall outcome. So guys, I'll pick a number less than -5. Let's go -6. Opposite of -6 is 6. 6 minus 5. I've got a positive numerator, and then -6 plus 3 is negative, so a negative denominator. That's how I play these rationals out. This would be my big fraction line in the middle. Positive over negative, anywhere in this interval, obviously produces a negative. And that's not the outcome that we were looking for. We're looking for greater than 0. We're looking for positive. Hey, let's go ahead and pick something between -5 and -3. -4 works out nicely. Opposite of -4 is 4. 4 minus 5, that's negative. -4 plus 3, that's negative. And so I have a negative numerator, divide by negative denominator, it's positive. And yes, that's one of our outcomes. Cool. Let's pick something bigger than -3. 0 works great. 0 minus 5, negative. 0 plus 3, positive. Negative over positive is negative. And now you can see exactly how this plays out. It's just so nice of a process because I've already laid out everything, 99% of the work done. I just have to interpret. And there's our solution set right there. So again, in order to kind of make this work, just one more time, you've got to bring it over, set it to 0, combine the fractions together, get it like this, and then it's yesterday's lesson, except instead of the factors being all multiplied together, you've got just numerator over denominator. See what the outcome is on the numerator, see what it is in the denominator. Cool. Let's go do 2 more. So it would be great if you could pause the video and try to get it where we have one fraction set to 0. Let's see if we can do that, and then come on back and see how you did. Okay, so here's what I did. Bring over the 1, and again, I do that. You don't have to, of course. Common denominator is x plus 1. That's beautiful. This doesn't change. Denominator didn't change, so numerator doesn't change. In this case, denominator changed by multiplying it by x plus 1. And so, guys, of course, numerator also multiply by x plus 1. All right, nice. Just be careful, always with subtraction. I see so many more mistakes with subtraction. I get 2x minus x is x, and then really the negative goes in. I get x minus 1 on top. Just be careful with that. And then greater than or equal. Fantastic. Let's go get some boundary points right here. So come from the numerator, come from the denominator. So here, guys, we get 1 as a boundary point. Here we get -1 as a boundary point. All right, now remember as we look here, we're looking for where this would be. Let's get to this stage right here, where it is greater than 0, so positive, or equal to 0 in this case. We're going to have to be a little careful on this one. So watch this in action. But I've got my boundary points in place. Here we go. What did we say? 1 and -1. Perfect. -1 is to the left, +1 is to the right. That looks great. Now, guys, run the 3 columns. Run them all. Intervals. And the factors, x minus 1 on top, x plus 1 down on the bottom. Those are the factors that I see in the numerator and denominator. And then, of course, the overall outcome. We want greater than, and then, of course, we will include the zeros here, but watch what that means. Okay, so I'm looking to the left of -1. Throw that in place if you would. I'm looking in between -1 and 1. Throw that in. And last, bigger than 1. Again, hopefully it's getting quicker, more efficient, whatever you call it there. And let's go put this in place. Less than -1. I'm going to pick -2. -2 minus 1, negative numerator. -2 plus 1, negative denominator. And outcome, of course, is positive. And yeah, I actually do want that one. All right. How about this? In between -1 and 1, let's go with 0. Put in 0 there. And again, it should be quick, guys. We should be at that stage where it really works nicely. And I'm seeing a negative outcome there. Not going to work. Bigger than 1, so let's go with 2. Positive on top. Positive on the bottom. Looking great. And that's positive right here. All right, so I am ready to put this in place. We want it greater than or equal to 0. So here's what I'm going to do. I'm going to do it wrong for just a second, and I want you to think about what's wrong and how to fix it. So trying to fall in line with yesterday's lesson, I would go ahead and say greater than or equal to 0. And so in this case, I would say x is less than or equal to -1, or x is greater than or equal to 1. All right, so here's the thing. I did everything really nice except write my final answer. So the question is, how to fix? What is wrong? And it's only a slight mistake, but what is wrong with my solution set up there? Take a look at it. Okay, now let's think about this for a sec. I wanted for this fraction to be greater than or equal to 0. Now here's what I would argue. In a fraction, if the numerator is 0, well, that makes the whole thing 0, right? We've seen that before, of course. So if x is 1, yeah, that's great. If x is 1, it makes this whole thing 0 right here. And so I do include that. This is good right here. But notice what else I included. I included -1 as part of my solution set. And if you go back and look in, guys, is -1 actually going to produce 0? No. Where did we get the -1 from? We got the -1 from the denominator, and the denominator of the fraction being 0 is not going to make the whole fraction 0. It's going to make the whole fraction undefined. And so as a result here, I can't just arbitrarily put the equals on, in this case. The denominator, or the boundary point from the denominator, doesn't make it 0. It makes it undefined. And so we have to exclude that, obviously. That is the perfect solution set right there. So just keep an eye on that. Numerators, yes, they're going to produce 0. Denominators, no. They produce vertical asymptotes, an undefined situation. All right, let's try one more. So this is good. This is actually already factored, and it's just set to 0. This is perfect. Oh, couldn't ask for anything more. One fraction, all factored form, and we're looking for where it's negative. We're looking for where it's less than 0. So let's go get the boundary points. From the top, I've got 4. From the bottom, I'm getting -2. Also from the bottom, is this going to produce a real number boundary point? Think about that real number line there. When I do x squared plus 1 equals 0, is that going to give me a real number that's going to affect positive versus negative? Nope. So guys, I'm only seeing these two, +4 and -2. All right, so let's get this in place. Follow through the last one, guys. You can do it. There it is. And let's go ahead. I'm going to go right over here and do this. So we have our situation at hand. And let's go 3 columns one more time. Intervals. Now, it's going to get a little weird here. I'm going to write it as it was. So this was x plus 2 as a factor and x squared plus 1 as a factor. So those are our factors. And then finally, we're looking for a negative outcome here. So let's see that in place. So everyone, less than negative 2, in between negative 2 and 4, bigger than 4. Let's get that going right up here. 1, and 2, and 3. All right, so we just want negative, and let's see it happen. So watch in this case, and again, there are a couple different ways to perceive this one, but I'm curious what's going to happen on the numerator. So in this case, I'm going to put in negative 3, just something less than negative 2. Negative 3 minus 4 is negative 7, but when I square negative 7, what type of answer am I going to get in the numerator? Well, squaring that negative produces a positive. And as a matter of fact, think about this. No matter what, as we work our way through, what's going to happen to that numerator? Should be positive. Well, let's see the denominator. Negative 3, so negative 3 plus 2 is a negative, and then still times something else down there. And look what happens in this little quadratic factor right here. If I do negative 3 and square it, I get 9, and 9 plus 1 is 10. And think about this. No matter what number I put in here, what am I always going to get? Positive. So we can kind of shortcut this a little bit, I'm hoping. But let's see. So guys, I have a positive on top. The denominator is going to turn out to be negative, right? Negative times negative. So a positive over a negative is negative. Cool. Let's go ahead and put in 0 for this one. 0 minus 4, but then square it. We already said this, always positive. 0 plus 2, positive. 0 squared plus 1, positive. So it looks like I've got that taken care of. Positive over a positive. Got it. Oh, and by the way, I neglected. Throw a little check mark on that one. Last one, guys, bigger than 4. 5 minus 4, square it. That's positive. 5 plus 2, positive. 5 squared plus 1. Oh, come on. Quicker, quicker, quicker. We've got it. And there it is. Now, we don't have to worry about any or equals here. So we don't have to include any particular boundaries. Again, the only one that we would include would be the 4, by the way. But in this case, it looks like we just want the negative outcome. And so I'm looking less than negative 2. All right, see, some great math that really goes with this. And also a very fascinating kind of concept, the idea behind you can't just multiply top and bottom by a variable because we don't know if it's positive or negative, and we don't know whether to switch the symbol or not. So follow those steps in order to make this work. Hey, great stuff. Please let me know as you do some practice problems if you have some issues. Thanks, of course, for listening.